Hi guys, it's your science teacher here with another video. This time I'm going to try and go through the whole of physics paper 1 with you guys. And I know that sounds like a lot, and it kind of is, but I'm going to try and keep it as concise as possible. Remember, if you do struggle with any of the content in this video, I do also make some shorter videos that go through these topics in a lot more detail. So without further ado, let's get started. First thing we are going to look at in this video is energy. And the first thing you've got to know about energy is energy cannot be created or destroyed. It can only be transformed forms. But what forms can energy exist in? We need to look at different types of energy stores. We say that anything that has movement energy has kinetic energy. Anything that has height has gravitational energy. Another store of energy can be elastic energy. When you stretch an elastic band, it's going to really want to return to its original shape. Another form of energy is chemical energy. An example of a chemical energy could be food that we eat. That's a chemical energy. Another type of energy is electrostatic. This is the force of attraction or repulsion between charged objects. We can also have sound energy, thermal energy, which is obviously heat, and we can have nuclear energy as well. But perhaps the most important one that we're going to look at is electrical energy. That'll come up a lot in physics. Now we've had a look at the main energy stores, we need to look about how they interact with one another. So here's an example. We have a radio here, and with a radio, it's going to transfer energy to different forms. The energy going into in a radio, if it's plugged into mains electricity, is electrical energy. If it's a battery radio, it's important to remember batteries give out chemical energy because it has chemicals inside it. But this electrical energy is going to be converted into sound, which is our useful energy from a radio. Now, sound is not the only energy that's going to come out of my radio, though. All electrical devices give off some heat. Now, this heat is not what we want from our radio, so we call this wasted energy. And from this, we can come up with an equation, which is the first equation we are going to look at, which is efficiency. And how efficient your object is the amount of useful energy divided by the total energy going into that appliance. Now, because energy is always conserved as well, if 100 joules of electrical energy are going into my appliance and 60 joules were coming out as sound, how much would be coming out as thermal? Yeah, you're right, it's 40 joules, isn't it? Because of the fact that energy cannot be created or destroyed. And this leads into my efficiency. This radio would be 60 joules divided by 100 joules, which is 0.6. And you can leave efficiency like this as a decimal, or you can turn it into a percent by timesing it by 100, and you could leave it as 60%. When energy is transferred from one store to another, we say that work has been done. To calculate the work done on an object when a force moves it, you can use the equation work done equals force times distance. Now, work done is sometimes called energy transferred as well. So this has the units joules, force has the units newtons, and distance has the units meters. At this stage, what I'm going to do is I'm going to tell you how I use calculation triangles as well, as we're going to encounter them a lot of times in this video. So what we have here is we have work done on top of my triangle and force and distance at the bottom. What you need to do to calculate one of the things in the triangle is cover it up. So for example, if you are wanting to calculate work done, what you need to do is cover up work done. And now you can see that force times distance is equal to work done. But what happens if I'm not wanting to calculate work done and I'm wanting to calculate the distance? And if I want to calculate distance, what I would need to do is cover up distance with my hand, and distance equals work done, and because it's over it, that means divide work done divided by force. Finally, what would happen if I wanted to calculate force? Well, I'd cover up force with my hand, and force will equal work done divided by distance. Another key equation for you to know is the gravitational potential energy. And this is the amount of energy gained when you go up in vertical height. And in order to calculate the gravitational potential energy, what you need to do is you need to do the mass times the gravity times the change in height. And this is one of them key equations again. And I'll just show you one last time how to use these rearrangement triangles. For example, look at H. If we wanted to calculate the gain in height of our material, you cover up height, and that equals gravitational potential energy divided by mass times gravity. And if I go over here, that is my equation that I got for this. Now, we don't have time for me to go through in detail every equation, so some of the equations I might just give to you just like this. A key thing though that examiners try and trick you out with gravitational potential energy questions is they often have things on a ramp, an object, and you have to remember that it's the vertical height above the ground that we use for gravitational potential energy. It's not the length of the ramp. So for example, if this ramp was 15 meters long but only 6 meters high, then 6 meters is what we use for the height, not the 15 meters length of the ramp. Two more energy stores we need to make sure we are remembering is our elastic and our kinetic as well. If we look at how to calculate kinetic energy first, I'll represent kinetic energy with EK and I'll represent elastic with EE. The way to calculate it is half times the mass of the object times the velocity squared. Remember, energy is always measured in joules, mass is measured in kilograms, and velocity is measured in meters per second. And there's a reason why I put these two equations together. It's because they're very similar. Elastic potential energy is half times spring constant times extension squared. And the spring constant is measured in newtons per meter, and x is measured in meters. And elastic energy is also measured in joules. Now, these rearrangements can be a little bit tricky, so I'll just do the ones for kinetic energy because elastic energy is exactly the same rearrangements because you can see that the parameters are exactly the same. So for example, kinetic energy, that's the easiest one to do. Kinetic energy is just simply half mv squared. To calculate the mass, it's a little bit more tricky, so let's cover up mass first. Mass equals, you've got EK on top divided by half times by V squared. And the hardest one, and I'm going to do it up here because I'm going to need a bit more space for this, is calculating V. The way I like to do this is by covering up my V squared and saying V squared equals EK divided by half times by M. And then to get rid of my squared, I square root. So V equals square root and put everything inside there. EK divided by half times by M. What you could now do is pause the video because I'm going to just show you the elastic potential energy rearrangement. So see if you could do that to calculate each parameter for elastic potential energy. All right, there you go. There's the rearrangement for the elastic potential energy as well. Now, what's important to remember is in energy transfers, you can actually go from one store to another. So for example, if you've got a slingshot, you start off with elastic energy and you're converting it to kinetic energy. So you might have a question which is calculate the velocity that a projectile is fired with from a slingshot. And what you'd first be expected to do is calculate the elastic potential energy of the projectile. And then this should equal the kinetic energy of your projectile as well. So you could calculate the velocity that it comes out at. If you want to see examples of me doing that, watch my topic videos, because in the P1, conservation and dissipation of energy, I go through an example just like that. And I do the same with gravitational energy being converted to kinetic energy. It's just key to remember when you do get a question like that, you're assuming that all of the energy is getting transferred from one store to another. There is one more equation that we need to know for this topic, and that is power. And power is the amount of energy transferred in a given time. So the way we calculate power is dead easy. Power is equal to energy divided by time. And power has one of my favorite units, which is watts. And remember that energy's units are joules and time is seconds. So a watt is equal to a joules per second. With electrical devices, it will sometimes want you to calculate the amount of kilowatt hours that are used as well, which is another way of saying energy transferred. And the way they do, the reason why they do that is because that's how they calculate how much you are paying for your electricity. So for example, you could work out if at home you have a 30-watt light bulb, and that light bulb is left on for 12 hours in the day, you could work out how much that light bulb is costing you in that day. Maybe a kilowatt hour costs 11p per kilowatt hour. So let's calculate how much it would cost to leave that on. First things first is you need to convert 30 watts into kilowatts. So the way to do that is to divide by 1,000. So you have 0.03 kilowatts. And if it's left on for 12 hours, you have used up 0.36 kilowatt hours. And then to work out how much you paid for it, you just times that by 11 pence. So it's 0.36 kilowatt hours times by 11p, and in total that has cost you 3.96 pence. But energy always round up, energy companies do, for the price, so that has cost you 4 pence. What we're now going to look at is the energy transferred through a material when something is heated. And if the particles are touching, we can say that conduction is taking place. And the way that conduction happens is you have particles touching, and those particles may be cold, but if they are next to, say for example, some warmer particles, what will happen is over time, them warm particles touching those cold particles will heat them up, and the heat will move by vibration. Imagine you put a metal spoon inside a cup of hot water. You wouldn't want to touch that metal spoon after it had been inside that cup of hot water because of the fact that the particles would have heated up. Even if they're not in direct contact with the water, the heat would travel through that metal really quickly, as metals are good conductors of heat. Another form of energy transfer is convection. And convection can happen in fluids because fluids can move round from place to place. And what happens with convection is you find that when you heat up particles, they become less dense. So therefore, they will heat up, rise, then they'll become more dense as they cool, and they will fall back down. This is what happens in your radiators. It's also what happens underneath the surface of the Earth. This is why we have our tectonic plates, is due to convection moving those tectonic plates around. And there's one more type of heat transfer called radiation. And radiation does not involve particles, it does not need them. The reason for this is because of the fact it involves waves. And in this topic, that's all you need to know really. When you get on to paper 2, then you start looking at the infrared radiation involved. Investigating energy transfers is incredibly important because we need to make sure that in our homes we keep all the heat in and we don't let cold air enter our house. So if we look at areas of the house which might lose heat quite rapidly, they're things like our roofs, our windows, our doors. We need to make sure that they contain something called insulators. These are things that are poor conductors. So if we look at some ways that we can insulate our house, the first one is double glazing. And double glazing windows works by having one panel of glass, then having a gap, then having another panel of glass. And the reason why this works is because of the fact there is an air gap in between. And the air gap is so important because air is a poor conductor because it's a gas, and therefore heat does not travel through it very well, and therefore the heat stays inside your house and doesn't go to the outside. Also, we have loft insulation, and loft insulation works very similarly to the double glazing windows. I don't know whether you've ever been in your lofts before, but you can see with that material it's very spongy, and spongy materials have lots of air gaps. It's incredibly very horrible if you do get that loft insulation on your skin. I don't advise you going up and checking. And the last thing we're going to look at is there is also insulation in your walls as well, which is called cavity wall insulation. And the way that cavity wall insulation works is it stops the convection currents happening in your walls. You can actually calculate the amount of energy needed to heat up a material, and this is called the specific heat capacity, and you need to know the exact definition of this. So this is a definition you should copy down. From this definition of it's the energy needed to raise 1 kilogram of the substance by 1 degree C, you can probably start to think about an equation that you would use to calculate specific heat capacity. So the specific heat capacity is given the symbol C in this equation. The energy needed to raise the mass by 1 degree C. So you've got here the mass. Here you've got the specific heat capacity, and here you've got the change in temperature. And of course, on top you have the energy transferred. So if you wanted to calculate the specific heat capacity of a material, what you'd need to do is you need to do the energy transferred divided by the mass times by the change in temperature. A few key things to remember about specific heat capacity is the larger the specific heat capacity, the more energy needed to heat it. So because of the fact that metals are incredibly good conductors of heat, they often have really low specific heat capacities. And if you look at a substance like water, water has quite a high specific heat capacity. In fact, you might be expected to remember water's specific heat capacity, which is around 4,200 joules per kilogram degrees C. Another key thing when doing these questions is remember it is the change in temperature you are looking at, not the final temperature or the starting temperature. So for example, if you're heating a substance from 20 degrees C to 100 degrees C, the change in temperature would equal 80 degrees C. Another kind of topic in energy is where we get our electrical energy from, and we look at ways that we could be sustainable in collecting our energy and also ways in which we are not being sustainable. So we look at a few finite resources, so resources that eventually will run out, and we also look at why we use these resources to make our electrical energy. So the main finite resources, sometimes called fossil fuels, because of the fact they were made over millions of years ago, are coal, oil, and natural gas. And they're called finite resources because of the fact they are being used at a quicker rate that they are being replenished. Because of the fact they are finite, this is causing a massive energy problem because we only have hundreds of years left of these fuel sources. As well as this, they are also polluting the environment. When these fossil fuels are combusted, meaning burnt, they release harmful gases into the environment, such as carbon dioxide, sulfur dioxide, carbon monoxide, and carbon particulates. And these are having drastic impacts on our environment. If we look at each of these gases individually, carbon dioxide contributes to the greenhouse effect, meaning that warms up the planet and it's having massive consequences. If you look at other topics in chemistry and biology, when we look at global warming, we'll do all the problems of the greenhouse effect. And sulfur dioxide causes acid rain, which obviously changes the pHs of soils and river ecosystems, having massive dramatic effects. And carbon monoxide is a toxic, poisonous gas. It's sometimes called the silent killer because you can't smell it. And there's carbon particulates, which causes global dimming. This just means that it gets a lot darker, and it's not nice to breathe in carbon as it's carcinogenic, meaning that it can cause cancer. In addition to the fact that these energy resources are running out, another problem is the fact that we have a growing population, so the demand on these energy resources is greater as well. So in this topic, we're going to kind of look at ways that we can try and meet our energy demands sustainably. But what does that word mean, sustainable? Sustainable means to meet the needs of the current generation without compromising future. So now we're going to look at more sustainable ways of creating energy, but these sustainable ways do sometimes have some disadvantages as well. And the reasons why we're still so dependent on these finite fossil fuels is the fact that we've used them for so many years and we've become dependent on using them now. And a lot of people are making a lot of money out of it, and it's using resources that we already know how to use. And maybe going into a more sustainable future, we need to start looking at things we are not so familiar with. Let's now look at some more sustainable resources of generating electricity and ways that are currently being investigated as potential sources of electricity for the future. We do already use a lot of these, but we perhaps maybe could use them some more in order to generate our base load. That just means the load that we depend on for our country. The first one is solar electricity. And the way that solar power works is it converts photons of light into electricity. This makes it sustainable as it's using the sun's energy to generate the electricity, not using a finite resource. The sun is going to be there for many, many more years to come. So it has some clear advantages. It's not going to put greenhouse gases into our atmosphere. As with all of the other techniques that we're going to look at for sustainable resources, they are not going to put greenhouse gases into the atmosphere. As well as this, sun is a free resource, isn't it? And it's quite reliable. In many parts of the world, it's very reliable that there is going to be some light throughout the day. Only at the poles, really, is it likely that you're not going to get some form of sunlight. So why do we not see solar panels everywhere in the UK? Why do we not see them on top of buildings everywhere, in farmland? Why do we look at alternative resources? Well, there's a few reasons for this. The materials used to build solar panels can be expensive. Also, they need quite a lot of land. They don't generate as much power as some other resources for the size that they take up. So let's look at another resource used to generate electricity, and we have the wind. And wind is a great resource because of the fact that is also free, isn't it? Free resource that's already there. Now, wind is not as reliable as the sun. You cannot predict wind patterns. So sometimes you can produce lots of electricity, sometimes you don't produce that much electricity. So it can be unreliable at times, and that's why it's not used as a baseload all around the world. In some really windy areas by the coast, you see lots of wind turbines because of the fact it's more likely that it's going to be windy there. In addition to that, people sometimes class them as an eyesore. People don't want them to be built close to their homes. Also, they cause a bit of noise pollution as well. They are quite loud. If you've ever stood near a wind turbine, they can be quite noisy at times. So let's look at another free resource as well, and they are the tides. So you can get tidal and wave power. They're two actually separate ways of generating electricity, and they use the force of the water coming into the shore in order to generate electricity. So that's converting the kinetic energy of the water into electricity. Obviously, it's a free resource again, isn't it? Because the water is already there. Also, it's incredibly reliable. You're always going to get the tides. And most days you're going to get waves of some sort coming in. As well as with solar panels, though, this is quite an expensive resource. Also, you can only use it around the coast. You can't use it further inland. It's going to have to be by the sea. So some landlocked countries cannot use tidal or wave power, can they? Let's now look at some more sustainable resources of generating electricity and ways that are currently being investigated as potential sources of electricity for the future. We do already use a lot of these, but we perhaps maybe could use them some more in order to generate our base load. That just means the load that we depend on for our country. The first one is solar electricity. And the way that solar power works is it converts photons of light into electricity. This makes it sustainable as it's using the sun's energy to generate the electricity, not using a finite resource. The sun is going to be there for many, many more years to come. So it has some clear advantages. It's not going to put greenhouse gases into our atmosphere. As with all of the other techniques that we're going to look at for sustainable resources, they are not going to put greenhouse gases into the atmosphere. As well as this, sun is a free resource, isn't it? And it's quite reliable. In many parts of the world, it's very reliable that there is going to be some light throughout the day. Only at the poles, really, is it likely that you're not going to get some form of sunlight. So why do we not see solar panels everywhere in the UK? Why do we not see them on top of buildings everywhere, in farmland? Why do we look at alternative resources? Well, there's a few reasons for this. The materials used to build solar panels can be expensive. Also, they need quite a lot of land. They don't generate as much power as some other resources for the size that they take up. So let's look at another resource used to generate electricity, and we have the wind. And wind is a great resource because of the fact that is also free, isn't it? Free resource that's already there. Now, wind is not as reliable as the sun. You cannot predict wind patterns. So sometimes you can produce lots of electricity, sometimes you don't produce that much electricity. So it can be unreliable at times, and that's why it's not used as a base load all around the world. In some really windy areas by the coast, you see lots of wind turbines because of the fact it's more likely that it's going to be windy there. In addition to that, people sometimes class them as an eyesore. People don't want them to be built close to their homes. Also, they cause a bit of noise pollution as well. They are quite loud. If you've ever stood near a wind turbine, they can be quite noisy at times. So let's look at another free resource as well, and they are the tides. So you can get tidal and wave power. They're two actually separate ways of generating electricity, and they use the force of the water coming into the shore in order to generate electricity. So that's converting the kinetic energy of the water into electricity. Obviously, it's a free resource again, isn't it? Because the water is already there. Also, it's incredibly reliable. You're always going to get the tides. And most days you're going to get waves of some sort coming in. As well as with solar panels, though, this is quite an expensive resource. Also, you can only use it around the coast. You can't use it further inland. It's going to have to be by the sea. So some landlocked countries cannot use tidal or wave power, can they? So we've had a look at some different types of energy resources that we can use a lot more sustainably. And here's an example of another one down here, geothermal energy, which converts the Earth's heat into electricity. And this resource would be absolutely fantastic. The reason why is because of the fact there's no fossil fuels involved. It produces loads and loads of energy. It's really, really good. In fact, in Iceland, they get nearly 80% of their electricity from geothermal energy. And the way it works is you just drill down into the hotter parts of the Earth, the upper mantle, and it heats up steam, which turns a turbine and generates electricity, which is fantastic. But the reason why we cannot use it all over the world is because of the fact it only really is useful by tectonic plate boundaries. Because of the fact there's not many places where the Earth's crust is thin enough for you to utilize this resource and drill far enough down into the Earth's crust. So the key thing to these sustainable Earths So the key thing to these ways of generating electricity is they all have their pros, they all have their cons, and that's why we use such a wide variety of them to generate our electricity. But we also use fuels in order to power other things like our cars. And looking at resources that we use for powering our cars is also important. At the minute, currently, we use a lot of petrol and diesel. These are finite resources which also come from crude oil. And you'll look a lot about crude oil in chemistry paper 2. So how can we look at making this more sustainable? Well, the way we can do that is by investing in biofuels. And the reason why biofuels are going to be a massive thing for the future is the fact they use plants. And you grow these plants and they produce this oil that can be burnt in a car. They put that carbon dioxide they've collected during their life through photosynthesis back into the environment. So therefore, they are called carbon neutral. The only real problem with biofuels is the fact that they take up a lot of space as well. And this is why there is a lot of money and investment going into electric cars as well, and also some hydrogen cars as well. We're nearly halfway through the video now, so I suggest this would be a good time to get yourself a cup of coffee or have a little bit of a break. But if you are not that type of person and you just want to get through it, that's completely fine. And we will get into the next topic, which is electricity. And the first thing I'm going to do with electricity is use a model to explain electricity, because I think electricity is quite a hard concept to grasp. So the way I like to view electricity is I like to view it like a river. And the reason why I like to do this is because I can then describe the key terms. For example, voltage is the push of charge around a circuit. And I like to think of the voltage in a river like the steepness of my river, the thing that is going to keep my water flowing. Then the current of electricity is the amount of charge passing a certain point per second. And I like to think of the water like charge moving around that river and the amount of charge passing per second. In fact, in a river, they often do describe the current as the amount of water passing per second as well. And then finally, another key term is resistance. And that is things that obstruct charge going around a circuit. Now, in a river, there's lots of things that can obstruct the water moving, isn't there? Like rocks and boulders and twists and turns. And the same thing applies to electricity moving around the circuit. It's also important to know what these different parameters are measured in as well. Voltage is measured in volts, current is measured in amps, and resistance is measured in this unit you might not have seen before, which is ohms. In the topic of electricity, we often use circuit symbols in order to show what we have present in a circuit, because it would take us far too long to draw out everything that is inside our circuit. So we need to remember some key circuit symbols, and I'm going to go through a few of them now. I'm not going to go through all of them because of the fact it would take too long. I'm just going to go through some ones that you may not have encountered until your GCSE. And the first one is this. It's a diode. And what happens with a diode is it only allows current to flow in one direction. Not the band, of course, we're still talking about electricity. As well as a diode, if you put a circle around that diode and you do a couple of arrows going away from it, that shows that it is a light emitting diode. And you've probably seen LED lights before. That's all that means. I've also drawn 3 different types of resistor here as well, and this one is a variable resistor, so it will vary the resistance inside a circuit. Underneath it I have a thermistor, which varies resistance based on heat. Used in some smoke alarms because of the fact it can sense whether it's got hotter or not, and then it can ring if there's less resistance in the wire. And then finally down here I have a light dependent resistor. These are often used in security cameras, so that it knows how much light to add to certain images in order to see things in the dark. Now, what do these actually look like in a circuit? When we're drawing out circuits, we usually start with something to push current around the circuit. So we'll draw a cell. If I draw another cell next to it, now I have a battery in there. And let's draw in my circuit a diode, so it only is allowing current in one direction. And I could also have in my circuit a variable resistor to vary the resistance. And I'm also going to have in there a light bulb. A light bulb is shown with a cross. You should remember that one from your time in Key Stage 3. And we will have a way to measure the current, and current is measured with an ammeter. And I will also use something to measure the voltage, which is a voltmeter. But what I want to show you is how I put this ammeter and voltmeter into my circuit. I put my ammeter in circuit in series and my voltmeter in parallel. And we're going to look in detail to what these mean. Series circuit, there is only one path for the current to go. And there's some key things you need to know about different series circuits. The first thing is the current is the same everywhere in a series circuit. So for example, if this ammeter was reading 2 amps, then this ammeter here would also read 2 amps, and this ammeter here would also read 2 amps. Voltage, however, is not the same everywhere in your circuit. It splits up. So for example, if this is a 3 volt battery here, I've got a 3 volt cell, then this will be a 1.5 volts, and this will read 1.5 volts as well. If they are identical bulbs, that's what you will get. The resistance in the series circuit is also quite easy to calculate. If this is a 10 ohm bulb and this is a 10 ohm bulb, my total resistance for that circuit would just equal 20 ohms. You just add them together. Here I have the opposite of a series circuit, which is a parallel circuit, which just means that you've got multiple paths for the current. So when we looked at series circuit, we noticed that the current was the same in all positions, but when there's multiple paths for the current to follow, we'll see what effect that has. So I said that there was 2 amps of current coming in to my circuit. Well, it's going to split up now. I've got 1 amp that will go down this road, 1 amp that will go down this road. And they rejoin here at this one as well. So once they get to this section here, they rejoin up. So you have half coming down and they rejoin here. The voltage, however, is different to a series circuit. The voltage does not split. So if we look and keep the batteries the same voltage, so they've said that these were 3 volt batteries, so we've got 6 volts coming in. This one here will be 6 volts and this one here will be 6 volts. The voltage in a parallel circuit is the same at all points. But what about resistance? Resistance, we looked at that for the last one. You just simply added it up, didn't you? However, the total resistance for this circuit is harder to calculate. What you need to use is this equation. The 1 over the total resistance equals 1 over R1 plus 1 over R2. And if there's any more resistors in, then you just add them on as well. So here you've got 1 over total will equal 1 over 10 plus 1 over 10. So that will be 1 over total equals 1 0.2, because 0.1 plus 0.1 equals 0.2. So then if you do 1 over 0.2, that'll give you the total resistance, which for this example will be 5 ohms. Now you might be saying, why do you use parallel circuits? They look a lot more complicated than a series circuit, and you're correct, they are a bit more complicated. But the reason why we use parallel circuits is because of the fact that if one appliance breaks in that circuit, then they all don't go out. For example, if this was a light bulb and not a resistor here, and this was a light bulb as well, if this light bulb was to blow, then this light bulb would stay lit up. So that's why we use parallel circuits a lot. A lot of the electricity that we use inside of our home comes from plug sockets, and this is usually at quite high voltage. And the next bit of the topic, we're going to look at how we stay safe with electricity and what type of electricity is actually used inside of our homes. And the type that is most used inside homes is something called alternating current. This is anything that is an electrical device that is plugged in at the wall, and alternating current periodically changes direction. It almost looks like a wave if you put it into an oscilloscope. An oscilloscope is something where you can track the current, and that's called alternating current. The reason why we use AC current in our homes is because of the fact that alternating current is quite easy to change the voltage of. And for mains electricity, this is of course something that's really important, as that electricity might have to travel a long distance. And for it to travel a long distance, often you want to have its voltage quite high. This will decrease the resistance, and therefore you'll lose less electricity as it travels longer distances. Inside the home, you also need to know the voltage and the frequency of alternating current from the mains electricity. And alternating current for mains electricity comes in at 230 volts in the UK. So that's what it would look like on an oscilloscope. And also it changes direction 50 times per second, so it has a frequency at 50 hertz. You can in fact calculate the period of the wave, so how long it takes for it to change direction. That's just 1 divided by 50, and that will tell you the period of the wave, which is in the topic of waves as well, which is of course 0.02 seconds. The type of electricity that comes out of batteries doesn't change direction, and this is what's known as direct current. And the reason why it's called direct current is because it only goes in one direction. And often with direct current, it's at a lower voltage, as it's often coming out of a battery. So if you were to look at an oscilloscope reading, its voltage isn't going to change, and it's just going to look like that. Of course, we do use DC current in many different appliances, such as things like your mobile phone. Your mobile phone will have a battery in it. So when you charge up that battery, out of that battery comes direct current. So direct current is incredibly useful in thousands of different appliances. But unfortunately, it did not win the electricity war between Edison and Tesla. AC current is what we do use in our homes and what comes out of our plug sockets. Because the voltage coming out of our mains electricity is quite high, our plug needs to be designed in order to be safe with such high voltages. And the way it's done that is by it has 3 different wires, all different coloured, and we need to know what each wire does. So the first one we're going to look at is this brown wire over here, and this brown wire is called the live wire. And the live wire is what carries a current to the appliance. There are also 2 other wires. There is this neutral wire, which is blue, and the neutral wire that carries the current from the appliance back to the plug. So you might be saying, well, what does the other wire do? It's the electricity's gone to the appliance and the electricity's come back from the appliance, so why have this third wire? And in fact, in European countries, there is no other wire. You might have noticed in them plug sockets there's only 2 pins, and that's because they don't have this other feature. This is a safety feature on our UK plugs, and it's called the earth wire, and it's green and yellow. And this earth wire is only useful if there is a fault in the appliance. What it will do is it has a really low resistance, and it will carry the current instead of through a person's body. If they touch the metal appliance, it will carry it from the appliance to the earth through the earth wire. There is another safety feature on this plug as well, and that is the fuse. And what happens with the fuse is if the current becomes too high through the plug, it will break. So the way it does that is it has a real thin piece of metal wire that will heat up. It has really high resistance, so it heats up and breaks, and this means that electricity will no longer flow through the live wire. Some plugs that don't contain the earth wire are doubly insulated. This means that they just contain plastic, and these appliances don't need the earth wire, and that's also important for us to remember. The next thing to look at is a bit of particle physics, and the best place to start in this topic is by looking at the 3 states of matter. And it's important to remember that everything is made of particles, and particles can come in all shapes and sizes. But particles can be arranged in 3 main categories. They can be arranged as a solid, as a liquid, or as a gas, as I've labelled in this. So let's have a look at the 3 states of matter and how the particles are arranged in each of them. So if we look at the solid, they are all in neat rows and columns. And the particles can't move, they are in a fixed position. This means even if I heat them, they will not move, they can just vibrate when heated. Now, in a liquid, you can see that not all the particles are in rows and columns. They're not in a regular pattern anymore. However, it is still important to remember that the particles do still touch. Now, because of the fact that the particles are no longer in a regular pattern, they can show a few more properties. A liquid can flow, and it will take the shape of a container. Just think, if you pour a cup of tea, your water has gone from the shape of the kettle into the shape of your mug. And lastly, probably the most interesting state of matter is gas, where the particles are no longer touching. And because they're no longer touching, they will fill up the space. They will fill up any container that they are put in. Because of the fact they move randomly. We need to also know the names of these state changes. So a solid going to a liquid, well, that is called melting. Just think about if you put chocolate in the microwave, it's going to melt. Then from a liquid to a gas, that is called evaporation. Now, when a whole body of liquid is evaporating, we call that boiling. Don't get the two confused. And a gas going to a liquid, that's called condensing or condensation. And then going from a liquid to a solid, that is called freezing. Now, you might be asked going all the way from a solid to gas, and don't be too confused if you do see that. That is called sublimation. And we need to know what actually it looks like if you take a solid, you heat it up and it changes state to a liquid and then changes state into a gas, what that looks like over time. So over here I've drawn the axis of a graph showing a heating curve. Now a cooling curve is just completely the opposite, and you can show that going from a gas to a solid. Remember, if you do want to watch any of these things in more detail, watch my whole topic videos. But let's just look at a heating curve. When you heat up a solid, it will increase its temperature uniformly until you get to a certain point where it starts to change state. And when it starts to change state, you kind of get a relaxation. It stops increasing in temperature. And this is because it requires energy to change state. Look at a solid, it's all in neat rows and columns, and you're disrupting that structure. That's going to require energy. And that's why it flattens out. And then it's going to start increasing in temperature again, and then it's going to flatten out. Now this line's going to be more flat. It's going to take longer for this change of state. And the reason for that is because, look, all the particles are touching here and you're ripping them all apart. You're breaking that intermolecular forces between them. So that's why this change of state can take more energy. Now, the amount of energy to change state is called the latent heat. And this, for the melting, is the latent heat of fusion. And for the boiling, that's called the latent heat of vaporization. You can calculate the specific latent heat of vaporization or the latent heat of fusing, and use an equation. You will actually get given this equation in your exam, and this is the energy required is the mass times the specific latent heat, remember that the latent heat of fusion is the melting, so you can calculate fusion using this practical setup here. You've got a joule meter which measures energy, and what you could do is calculate the mass of ice changing to water dead easily by just heating up that ice, measuring the water, maybe having a balance where you can measure the mass of it, and there you could calculate the energy required to change state. And the same over here, it's the same equation. Energy is mass times specific latent heat. But remember, this is for vaporization here. You've got the heater, it's in a beaker of liquid. That liquid's going to evaporate off, and it's going to read you the energy on this joule meter here. Often you won't actually have a chance to do this practical in school, but it's important to know that it could come up. It probably wouldn't want you to know how to carry it out, but it might come up and they might actually ask you to calculate specific latent heat. So it's important to kind of know what the L represents here. That's the latent heat. The E represents energy. Remember, energy is measured in joules, and then the M for mass. Looking at gas in more detail, I said that gases occupy all the volume of a container that they are put in. And this is because of the fact that they move in all directions. Now, when they bounce into the walls of the container, they will put a pressure on it. The more collisions the particles have with the walls of the container, the more pressure there will be. So, how can I increase the pressure of a gas? Well, I can do three different things. What I could do is I could increase the temperature, as shown here, and if you look at the particles in the bottom square, you can see that they're moving more. The arrows are larger. That's indicating they are moving much faster. Or I could increase the amount of particles as shown here, and you can see that I've got more particles down here. There are obviously going to be more collisions with the wall of the container, and that's going to increase the pressure. Or finally, what I could do is decrease the volume of my container. Think of if you were to stand on a balloon, what would happen? And if you did that, you could actually cause the balloon to pop when the pressure gets so big on the walls of that container. Also in this topic, we also investigate something called density, which is how closely together particles are packed. And in order to calculate density, you use this equation here. I know this slide is a bit packed and I don't usually do this, but remember, I'm trying to go through as quickly as possible. So the density is equal to the mass divided by the volume. And this is something you're going to have to be careful with, because sometimes they try and trick you with meters cubed and decimeters cubed, and you need to be able to freely convert between the two. So I always remember that 1 meter cubed equals 1000 decimeters cubed. And it's really easy to calculate the density of a regular shape. Look over here, for example, at this cube. This cube has side lengths of 2 meters. So in order to calculate the volume of that cube, all you need to do is times them together and you get 8 meters cubed. And if it has a mass of 1 kilogram, this cube, then it would have density of 0.125 kilograms per meters cubed. However, not everything is a perfect shape. It's not perfectly symmetrical. We don't live in a perfect world, people. We have some things where we don't know the shape, we don't know the volume of it very easily. We can't calculate it by a simple calculation. Look at this rock, for example. So we still want to calculate its density, but how do we go about calculating its volume? Well, you can use something called a eureka can. And a eureka can is where you place it in water, and what happens is the volume of water overspills when you put that rock in, and you can collect that water in a measuring cylinder. Also, what you could do is just place the rock into a measuring cylinder if it does fit, and you will notice the volume of water goes up. That's because of the fact that the volume of water displaced is equal to the volume of an object. And this is called Archimedes' principle. And history states that he found out this when he got into his bathtub. He found out that the volume of water went up, and he said he noticed that it was the same as his volume. And apparently myth states that he ran through town shouting Eureka, and that's why the instrument used to calculate density is called a Eureka can. We are on the home straight, people. We are on the last topic now in physics paper 1, and this is radioactivity, perhaps my favorite topic in the whole of physics paper 1. And radioactivity is a property of atoms. And what radioactivity is it's heavy or unstable nuclei breaking down spontaneously. And it's important in this topic to remember what actually makes up an atom. I know this is chemistry, and this is where there is kind of a bit of overlap. So I'll just draw a quick atom of helium here. So if you've got the positive protons and I've got the neutral neutrons next to it, and around the outside I've got the negatively charged electrons. Remember, neutral neutrons, you have positive protons, and you have them negative electrons. Now, there is 3 different types of radioactive decay that nuclei can undergo. And the nuclei, by that I mean the central part of the atom. That's what's so the protons and the neutrons. And the first type of decay we will look at is alpha decay. And alpha decay is incredibly interesting because of the fact that it loses a whole helium nuclei. So you have a really heavy nucleus and it gets rid of a whole helium nuclei. And the way I like to represent it is like this. So if I just put a random element, and we'll just call it X, and it will have atomic mass of Z and an atomic number of Y. This is just completely random, of course. It will lose a helium nuclei. And this is also sometimes called an alpha particle and can be given the symbol like this. You might see it written like this. But now you've got to know what element it will make. So the atomic number will have gone down by 2. So it will have made a completely new element. It will make a new element, we'll call that W. And this bottom number will have gone down by 2. And this top number will have gone down by 4, Z minus 4. If I show you a specific example, it's easier to understand. So let's look at, for example, Pu is a radioactive isotope, and it has the number, if you find it in the periodic table, it has the atomic number 94, and the radioactive nuclei has the atomic mass 239. Now they're usually isotopes, heavy isotopes of the atom, and if you remember from chemistry, an isotope is something that has a different number of neutrons. The atomic mass can change. So let's think about the products that I'm going to make. Well, it's going to make a helium nuclei, isn't it? And then the bottom number is going to go down by 2, so that's going to be 92, and the top number is going to go down by 5, which is going to be 235. And if I find this number 92 on the periodic table, that's the important number, then I will find out that that is uranium. Now, there is another type of radioactive decay that causes change to the nuclei, which is beta decay, and we're going to look at that right now. And what happens in beta decay is one of the neutrons in the nucleus is changed into a proton and a high energy electron is released, sometimes called a beta particle. So let's have a look at what that does. And we'll look at a general equation first, and we'll use the same kind of format as above. So we'll use our element X, which has the atomic mass Y, the atomic number of Y, and atomic mass of Z, and that's going to release a beta particle, which doesn't have atomic mass, but it does have a -1 atomic number. We call that, just kind of balances out my equation, and it releases also a new element, which we will call W. And the bottom number actually goes up by 1 and the atomic mass doesn't change. So let's have a look at an example, and carbon-14 is a radioactive nuclei which is used in carbon dating, in fact, and it will undergo beta decay. So the first thing that's going to be emitted, of course, is my beta particle, that high energy electron. And let's look at what happens now. So the bottom number is going to go up by 1 because I'm making a proton. So it's going to change element. Now it is nitrogen and the atomic mass stays the same. And finally, we have something called gamma decay. And gamma decay is the easiest one to look at because nothing really changes inside the nucleus. It's an electromagnetic wave that is released. You'll remember from the topic of waves in paper 2, we look at gamma waves, and that is what is being released. And usually it accompanies alpha and beta decay. So if I look at some alpha decay, maybe from uranium-235, that is a unstable isotope. So let's have a look at uranium-235 undergoing gamma decay, and all that's going to come off is I'm going to still have my uranium-235, but I'm also going to have some gamma radiation. Alright, so we've now looked at the 3 different types of radiation, and now we're going to look at some cool properties about each of them. So the first one is alpha radiation, and if you look at this diagram that I've drawn, you can see that alpha radiation can be stopped by paper. This is because it is the least penetrating out of all of the three types of radiation. Also, it is the most ionizing. Now you might say, what does this word ionizing mean? And if you think back to chemistry, you'll remember to make an ion means knocking electrons out, and that's basically what these forms of radiation actually do. And ionizing cells can cause cells to die in the body, so it's not very good. Alpha radiation, if it gets inside your body, say if it's digested or it gets through into your bloodstream, it can be incredibly dangerous. However, if it's outside the body, alpha radiation is usually not considered too much of a threat because of the fact it's so not very penetrating, it won't even travel through your skin. Now, if we go all the way to gamma radiation, you can see beta's kind of medium penetrating power and the medium ionizing amount. If we look at gamma though, gamma is the most penetrating out of the radioactive sources, and it is also the least ionizing. To do this practical, you would have to use something called a Geiger counter, and a Geiger counter measures the activity of a radioactive source. Basically, it just has particles inside it that can become ionized, and this can detect radioactivity. And even if you place this Geiger counter there without any of these radioactive sources, you will still get some clicking. This is because of the fact there is something called background radiation. And the sources of these background radiation come from things like rocks and buildings, anything that's decomposing. All the medical equipment making X-rays, that causes some forms of radioactivity, and you also get some background radiation from space. When looking at a radioactive source, it's incredibly important to know that radioactive source half-life. And the half-life is the time for the number of radioactive nuclei to fall by half. Here you can see that this radioactive material has quite a short half-life because it's only measured in minutes. Some radioactive materials have half-lives of thousands of years. But let's have a look. So this could be the number of radioactive nuclei in the millions, probably is going to be that. And you can see that it starts off at, say, 1 million radioactive nuclei, and it takes 2 minutes to half to go to 0.5. And you'll notice that the half-life never changes. So if you go to 0.25, that's at 4. And you can even half it again and go to 0.125. And you'll notice that that is at 6. So the half-life never changes of this material. And that's why you get this exponential curve. What do we also notice from this graph though? What we notice is if we started at 1 million radioactive nuclei and it's gone down to a half, then it's gone down to 0.25, then 0.125. What you'll notice each time we reach a half-life, the number of radioactive nuclei halves. So I start off with, I have half, and then it goes to a quarter of the radioactive nuclei that I started with, then an eighth, then a 16th, and so on. Because of this rule, we could calculate the age of a sample if we know the sample's half-life and we know how much is remaining. Alright, we've now covered everything in Physics Paper 1. You have done awesome getting yourself to the end of this video, so give yourself a massive pat on the back, and I wish you all the best of luck with your Physics Paper 1 exam. Remember, if you did like the video, please drop it a like and subscribe to this channel.